in this flow, we are going to envisage and we are to outline and demonstrate how the capacity of distributing computation in terms of monitoring detection of events with AI in the edge can be supported and helped by the execution of serverless function on demand to comply with certain reactions that are required. For this, we are going to first show how a serverless function can be created based on IRO's methodology and templating for a serverless technology OpenFaaS. Later, we will show you how everything is integrated in a portal and how changing some thresholds for detecting anomalies in certain time series monitored in nodes of the computing continuums trigger a reaction and pop a message to a user of the continuum. So starting, I will pass the floor to Joe McNamara from LMI to explain the creation of functions in OpenFaaS. Thank you.
Thank you, Nacho. So here on the screen, what we're looking at is the dashboard of the OpenFaaS component. The OpenFaaS component was used as the platform to build our embedded analytics tool upon. In our documentation, we go through a breakdown of a embedded analytics tool function. So all functions are created based on an AROS template. This creates a directory called function. It creates a Docker file, which is the image that the function will be containered in. We have an index, which is the handling the interfaces of the function, and we have requirements, which are libraries related to the operation of the Docker image. Inside the function directory, we have 4 more files. The first one is an initializer. This initializer is executed at the deployment stage of a function. The handler is the script of the function. So when a function is executed, the handler is triggered. We also have a metric reporter, which is a script designed for the pushing of in-function metrics to the Prometheus of the embedded analytics tool, which then can be visualized through Grafana. And finally, requirements is similar to the one above, but this one is in relation to the execution of the handler. So any libraries that are required for the execution of the handler script would be packaged in there. So the way we deploy our functions is through FaaS CLI. It's a terminal application provided from OpenFaaS. It provides 4 main functionality: the creation of a function, which references our AROS template, the building of the function into a Docker image, the pushing of the function to a Docker registry, which we have hosted through GitLab, and then finally the deployment of the function through the Embedded Analytics Tool Gateway, again hosted by OpenFaaS. So the first thing that we're going to look at is the creation of a embedded analytics tool function. So here we can take a function script and we can go to our terminal. Inside the terminal, we're going to create a new function. Function is going to be called EC001. We are going to use our AROS Python 3 Flask language. And we are actually going to set the prefix to be our registry component, which can be shown part of our common deployments, and then through our container registry. So we can take the same deployment as this, and we can drop it back into our script. So this is essentially telling our application where we want the function to be stored. And we're
Sorry,
going to
Joe,
store.
can you please make the font a bit bigger because it's difficult to read. Sorry.
Perhaps. No. Options, text.
Yeah, there. Yeah, much better. Thank you.
Okay. Oh yeah, that's a lot more visible. Okay, fast CLI EC001. We have our language, which is going to be relating back to our template, and we are specifying the location that we want our image to be pushed to. Okay, so I have triggered this in the wrong folder, so I will move into my functions folder where we have our template folder stored, which should be visible. Can't see the template folder. Template folder is there. So this symbol here symbolizes that we have now created an OpenFaaS function. We've created the folder EC001, and we've also created a YAML file which acts as the tag for the folder. So now when I move in, I should be able to see. Slightly can't see it. Hold on. No. Okay, so now that we have created our OpenFaaS function, we can step into the function EC001, and we can see the files that have been created as part of the system, as part of the template. So the next thing that we have to do is we have to step into our function, and we have to update our handler with the script that we wish to run. So we can step into our functions, EC001, step into our handler, and we will update this handler with a new handler. And that will look like this. So, Nacho, would you like to explain the function that we are deploying here?
Yes, of course. Thank you, Joe. So for showcasing the scenario of this flow that we want to demonstrate, basically the asynchronous serverless function that we want our cloud system to trigger when an event happens consists of popping into the UI, into the portal where a continuum administrator, a user of the system, should see and should confirm and provide the information that specific infrastructure element of the continuum has detected an anomaly on the time series of the CPU disk usage or the RAM usage or the disk usage of the specific node, excuse me. Then what we have inserted here in Python code, it's a capacity to get a token via kcloak in order to use the portal and to trigger the API of the backend of this portal. This is done because Aeros works under a global identification management system, which is kcloak, where it retrieves the capacity of a user to use these APIs. Once this is granted, then a notification is triggered through the API in the first function. Therefore, in conclusion, we have created here the code so that this reaction to such event will take place. This has been designed in a modular way so that any developer, upon any kind of circumstance in the continuum, such as another detection, could program their own reaction to it, giving us a lot of flexibility moving forward. Therefore, now we will start seeing, once this function is there, how this actually works. So I just pass the floor again to you, Joe.
Okay, so now that we have updated and saved our handler, we should be able to step back into our command line, and we will look to push our script or our handler to the OpenFaaS, or sorry, not to the OpenFaaS, to the GitLab container registry that we are running for our project. So here I'm going to take an example script from, or sorry, another command from our function deployment. And I am going to update this to fit our new function name. So the name of the function that I wish to push, I will just have to step back out of the function first. CD. Oh. So there it is. So we are going to push now our function. So our function name is EC001. And we've attached a Grafana user and a Grafana password parameters to allow us to access the visualization element of the embedded Landix tool. So again, it's deploying the same function, so it's relatively quick. We have an EC001. We can check the Kubernetes again. It is creating the container, and our container is now running. And we should see this reflected in the status of our function ready. So to trigger this function, we can paste in an example body that we have here. And we can trigger this, and we can get back a positive response. A 200 response indicates that a successful request and response has been triggered by the function.
So now just move to the, thank you very much, Joe. Just move to the actual demonstration of what happens or what can happen in a continue, and how it, via the usage of this function triggered automatically by the system, pops a notification. So for that, I pass the floor to my colleague Raul to explain how to pre-configure this behavior.
Here we have the home of the AROS management portal, and we can access to the domains. In this moment, now we have two domains in the AROS continuum. If we see the Cloudflare domain, we can list in this moment 4 infrastructure elements: the infrastructure element node 0, node 1, node 8, and node 7. And here we have information related with every infrastructure element. For example, the CPU architecture, the CPU core, RAM capacity, even the trust score, and the status. If we click in the CPU anomaly detection parameters, here we can change it, and we can set the values 1, 0, 1, 1, okay, in the CPU. And we can do the same with the RAM anomaly detection parameters. With this change, we force to the self-optimization and adaptation to detect more easily and more fast the anomalies related with the CPU and the RAM in the node 7. Okay. Now, through the Self API, we have changed the values related with the CPU and with the RAM anomalies in the node 7, and we can see the test of the AC001 function. As we can see, the notification received in the AROS management portal, okay, related with the AC001. Okay. Now I pass the floor to Zosha.
Okay. Hello. So just let me show my screen. I will briefly describe how the model works. So essentially, on this diagram, you can see the general scope of the anomaly detection model. On the input data, we are receiving the, here it's meant the feature vector, but it's actually the current infrastructure element state. We are receiving that from the self-awareness module. In the data entry point, we basically filter all the features that are important in case of anomaly detection. So in this case, we are interested in the CPU usage, RAM usage, and the disk usage. And also we are getting here the model parameters, which are stored within the model configuration. You can see that the anomaly detection model is actually divided into 3 sub-models. And also for each this sub-model, we can separately configure the model parameters. Each of these models is responsible for detecting anomalies that are strictly connected, for example, only with CPU, only with memory, and only with disk usage. From the internal perspective, these models use the statistical-based algorithm that essentially recursively computes the data density. Based on the new infrastructure element data, it computes what is the current mean and the scalar product of the current metric, and also uses the previous mean and scalar product. Those are only the 2 values that are stored within the local cache. In order to later on compute a new density. Then it compares the difference in the current density and the previous density. And if it exceeds the average density, the state is considered anomalous. As Raul mentioned, we are also using a few parameters to be able to kind of tune the sensitivity of the model. And in this case, specifically, we are using the tolerance threshold for the anomalies and the normal state, and the windows for the anomaly and normal state. In terms of the tolerance threshold, it basically is the confidence that we should make a transition between a normal and anomalous state. So in case of the threshold set for the anomaly, the higher the threshold is, the more sensitive our model will be. And the window for the anomaly at normal describes how many consecutive observations have to appear in a row and be considered, for example, an anomaly, in order for our model to switch the state and actually proceed with the information that an anomaly occurred. And after our model detects any kind of anomaly, those anomalies are considered separately. They are mapped to their specific codes that are recognizable by the self-orchestrator, and then are sent to the self-orchestrator so that this component can continue with further actions. Thank you.
Okay, thank you, Zosha. The self-orchestrator module is one of the 4 essential modules within the AEROS self-capability set. This module is composed by a rules engine, a facts generator, a trigger, and is wrapped by a REST API. In the REST API, here we have a list of endpoints related with rules and related with the alerts. This module uses a rules engine, and this rules engine evaluates a set of rules and evaluates a knowledge database. And this knowledge database is a set of facts. These facts come from the self-awareness. The self-awareness is subdivided into 2 submodules, and every submodule obtains information related with infrastructure element every, for example, every 5, 10, or 15 and soon seconds. This sampling frequency is updated using the self-optimization and adaptation module to reduce the resource utilization of the infrastructure element and the power consumption of the infrastructure element. When the information received from the both submodules of self-awareness is received in the self-orchestrator, the self-orchestrator transforms this information into facts and insert them in the rules engine and knowledge database. Then the users or the administrators of the system of the Eros continuum can insert rules in the rules engine through the Self-orchestrator API using these 6 endpoints. We can see, for example, we can see a rule using the name of the rule if we know this name. We can see a list of all the rules inside the rules engine. Of course, we can delete a rule by name. We can delete all the rules in one request. We can put a rule and we can post a rule. For example, if we post a rule, we should follow this JSON schema. This JSON schema is based in a module called JSON schema, and here we have the name of the rule, the conditions. We can see all the conditions where we can put here the name of the fact. This name should be a name of a fact inside the knowledge database of the rules engine. The operator, for example, less than, equals, more than, and the value. These are all the conditions, because we can introduce a lot of variables. Not only one fact. We can introduce, for example, in one rule we can introduce a lot of facts with a lot of combinations. For example, these 2 facts yes, but this fact no, or and or okay. And finally, we should introduce the event. Here in the event, we can put here, for example, the name of the error. This is the error code that the self-orchestrator requests to the OpenFaaS. For example, if we have a rule, and this rule should match with the CPU usage, we can set here, for example, if the CPU usage is greater than, for example, 70% of use, we should call to the, for example, AC001 or AC00X function in the OpenFaaS. This name of the function we should put here. And of course, if we want to modify a rule, we can use the put endpoint. The JSON schema is more or less the same. It's not the same because in the post rule we should introduce name, conditions, and event. But in the post rule we should introduce name, but we can introduce conditions, or we can introduce event to change one or the other parameter, or even we can introduce both parameters to change all the rule, of course. It's all allowed. Here. Okay. When the self-optimization and adaptation detects an anomaly, sends an alert to the self-orchestrator following the next JSON schema with the error code, for example, the AC001 function deployed in the OpenFaaS by Joe, and additional parameters if it's necessary. Okay, this attribute is a list of objects, and every object has 2 parameters, key and value parameter, to identify all of these attributes necessary to do the function. For example, if the AC001 function needs one attribute, call it, I don't know, for example, CPU value. Okay, we can put CPU value and the value of the CPU. By this way, we can introduce all the parameters that the function needs without to redefine the schema every time that we need to create a new function. Okay, 1 0 1 1, confirm, and the RAM anomaly 1 0 1 1, and confirm.
With these modifications, we are now setting some thresholds into the time series from the continuum from the infrastructure element that we have as users indicated as the moments where if the values of RAM usage or CPU usage go above or below for this in the prediction of the next values and in the detection of those, then we would like to be prompt about it as users. So if we let the system continue, the notifications will be prompted.
Okay, now we have a new notification. If we see this notification, we can see that the date is today, 7th of March of 2025. And the message received is a notification of type AC001. This notification comes from the AC001 function deployed in the OpenFaaS by Joe, and comes from the node 7 of Cloudflare infrastructure. This is the node where I had changed the parameters related with the CPU anomaly and the RAM anomaly.